Okay, so this is homework to part D. We're going to be deriving the 3D heat diffusion equation for spherical coordinates. In the previous videos, we did Cartesian and cylindrical coordinates. This is our spherical coordinate video. Also, you'll learn why I never became an artist in this video. So we'll start off, right? We have our plane here, right? We have our X, our Y, and our Z direction, right? And we'll have a vector going um, going here, right? That's our vector. I'm gonna undo this arrow, right? And so for the spherical, to get it spherical, we have to project that vector down into the XY plane, right? And so that kind of will be the spherical shape that makes it. And so the space that we'll be working in will be this one here, right? So we'll have this is our dr value, right? That's our change in radius. So that will also be projected down. And then that will have a change in the angle, right? So this is our d theta, right? And so that would go both ways, right? And that'll form our side, right? And that d theta value is then projected up into this space here, right? And so that kind of forms our 3D value, and then or our 2D value, and then we'll drop it down here, right? And so when we do this, we form like our spherical shell that we've made, right? And this is this projection here. Sorry, not that projection. This projection here, that is what this purple is. And that's our phi direction, right? So our phi direction is our purple. Now, since we have an R value and a theta value and a phi value, we have different units. And so in order to get the units all the same, like we did for cylindrical coordinates and theta, we have to multiply our d theta by r to get it out of radians. And then for our phi value, right, this one's a little bit more tricky. Since it's projected and um, it's rounded, we have to multiply not only by r, but we also have to multiply by the sine of the theta times our change in phi, and that accounts or that gets our phi value into the correct units for what is our volume, right? So our volume, like we did before, where in the Cartesian coordinates it was dx, dy, dz, and in cylindrical coordinates it was r d theta, dr, dz. This value for our volume will be dr, right? That's our first. Then it'll be r d theta, right? That's this value. And then our final value is our r sine theta d phi, right? And so from here, we'll move on like we did with Cartesian and cylindrical, and we will write down our energy storage and our energy generation terms, right? So energy storage, remember, that's our density. That's our density times our heat capacity times the change in temperature over change in time, and then times our volume value. So now it is dr, rd theta, r sine theta, d phi, right? And then we'll repeat that, right? If we remember our generation term, right, that was our heat diffusion, our change in heat diffusion times our volume, right? So it's Q times dr, rd theta, r sine theta d phi, right? And then our overall energy balance that we need, right? We have our energy storage equals our energy generation plus, and then it was our net heat flow for all three directions, right? So our net heat flow in the R direction plus the net heat flow in the theta direction plus the net heat flow in the phi direction, right? And so what was net heat flow, right? That was our Q in minus our Q out. So what we're going to do now is we're going to do the same thing that we did when doing Cartesian and cylindrical. We're going to do our Taylor series expansion to get our equations for our net heat flow, right? So we know that when we do this, we have the heat diffusion of the change in our value, right? So in this case, dr is similar to the heat diffusion in our R plus the change in our heat diffusion over the change in our radius, evaluated from our new radius to, or from the change in radius where that equals our old radius, all times dr, right? And then we can plug that in here. That's our Q out. Our Q in is just QR, right? So it's QR minus DQ, and I'm going to simplify this. It's going to be DQ at R. dr times dr, right? These cancel, and then we get the equation for net heat flow of R to be equal to the negative change in heat diffusion for R over the differential R times dr, right? And we can repeat that process for all three net heat flows. And I worked it out in the other two videos that we did this in, but for the sake of time, I'm just going to write it out because it is the same process as we did here, right? So it's theta equals minus dq theta over d theta times d theta. And then in the phi direction, again, the exact same thing, minus dq phi over d phi times the change in phi, right? And so those are our three net heat flows. Now we don't know what our Q, our QR, Q theta, and Q phi are. So now we're going to look at Fourier's law, right? Where Q equals minus K A dt dt. Nope, sorry, not dt. This value is whatever direction you're going in. Since I haven't specified a direction here, I'm just going to put X. Now it's not the X direction that we're going to be working in. Right, so we take this equation and we can use it for each of these equations. So Q in our R direction, so QR equals minus K. And then our area, right, it's everything that it's everything in our volume that's not the direction we're going in, right? So for QR, right, this is our R direction, so it's everything that's not, right? So it's this term here. So it's minus K times R d theta times R sine theta d phi, and then dt dr, right? We can repeat that for these next three, or these next two. So the Q theta equals minus K. All right, now we don't have this one, but we have this one, right? So it's these two. So it'll be dr and then times R sine theta d phi times dt d phi. So, sorry, dt d theta. And then for our phi, right? Our Q phi equals minus K. All right, now we do have this one here, but we don't have these two. So it'll be minus K times dr r d theta dt d phi, right? And so we can plug this in, right, into each of these equations. We get our net heat flow for each, right? So R of R, that equals d dr times our value up here, right? So minus K times r d theta times r sine theta d phi dt dr, right? And then we have our dr here, so we have to multiply the whole thing by dr, right? We do that for the next two, much like we did before, right? d theta minus K, and then it will be dr times r sine theta d phi times dt d theta times d theta. And then our phi direction, our last one here, is d phi times minus K dr r d theta dt d phi all times d phi. Right. So now that we have these three equations, we can take this, and I'm going to move it over to a new page here so that I have a little bit more room, right? So this is our overall energy balance, and these are our net heat flows that we know. So we will move these here. And then we will plug in, right? So our energy storage, that's what we started with, right? That is our density times our heat capacity times the change in temperature over the change in time times our volume. R or dr r d theta r sine d phi, and that equals, right, our E gen, right? That's our Q times our dr r d theta r sine theta d phi, right? And then we have our three net heat flows, right? So plus, oh, these are all negatives, right? So we'll copy these down. So this is our first one. Right. And then our second one. Sorry, this is taking, trying to avoid having to rewrite everything. Right. So we'll bring this one down as well. And then we will have our third one here. Now I'm going to drop this one down because I ran out of room. But we're adding all of these together. Right. And so when we look at this, the negative sign in each of these will cancel, right? Our negative, negative, right? So we can take that out of all of these. And then from here, what we're going to do is we're going to factor out our dr d theta and then d phi of each of these so that it looks a little bit easier, or it's a little bit easier to see what we're canceling out, right? So we have our rho c dt dt and then it's times r squared sine theta dr d theta d phi, right? R sine and then r, so that makes it r squared. And then we have our q r squared sine theta dr d theta d phi plus, and then we're going to factor out here, and we will have our we will have when we look at this, so this next this term here, right? The r's have to stay in because we're in terms of r, so it's d dr k r squared dt dr, and our sine theta d theta or dr, right? Our dr d theta d phi all are out. And then we can move on to this next one. I'm gonna move this up real quick. Right, we move on to the next one, d theta. So it's k, and then our sine has to stay in because there's a theta. So sine theta, right? And then dt d theta. And actually, in this, right, we have to multiply by our r and then our r sine theta, right? Because that gets it into the correct units. So when we do that, we can cancel out our r's here, right? And so that leaves then dr d theta d phi. And then finally, we have this equation up here where it'll be d phi d phi times k dt d phi, right? And then it'll be dr d theta d phi times 1 over sine theta, right? Because our r's cancel, but our sine doesn't, and that's in the denominator of this term here. And so that has to stay out. Okay, and so when we write it like this, we can see that each term, we can cancel out our dr d theta d phi, which is nice because that'll save us a little room when we are writing everything, right? So these all get canceled out. And then we're left with, on this right side, density times heat capacity dt dt times r squared sine theta. Now what we want is this term, so we will divide all of this stuff here over. And before we do that, one thing you can notice is each of these net heat flows has a K, and when we do this, we know that our K over rho C, right? That's our thermal diffusivity. So we can factor out a thermal diffusivity before we do all of this. And so when we look at this, right, we have our dt equals, right? So we'll start with this first term. So it'll be Q over rho C, and then our R squared and sine, right? Those cancel, right? So all that's left is the Q over our rho C plus, and then now I'll factor out our thermal diffusivity out of all three of those terms, and we will move on to the overarching, right? So we have our dr, and then we'll have our r squared dt dr, and then our sine cancels, but we still have our r squared, and we cannot cancel it with this r squared because this is in the derivative, right? So we'll have multiplied by 1 over r squared. And And then that's it for that term because we canceled out the sign. And then we can add our d theta times k, or not k, no k, we factor that out, sine theta dt d theta. All right, what are we left with? There's nothing on the outside here, so it'll be 1 over r squared times 1 over sine theta. Again, cannot cancel this sine theta because we're taking the derivative of the sine theta, and we have to account for that because we are in respect to theta. And then for this last term, we have our d phi times our k dt d phi, and that'll be times 1 over r squared times, and then we're dividing by sine. We have a 1 over sine here, so it'll be 1 over sine squared theta, right? And so when we look at this, we see that I accidentally left in a k here, right? This k is not there. We factored it out. And so this equation here, this is our 3D heat diffusion equation for spherical coordinates. It's a lot larger than the other two. There's less simplification that can be made. But we do see some common terms, right? We know that we have our Q over rho C, we have our thermal diffusivity, and it's just a matter of what changes within the net heat flows of each direction. So from here, we're going to move on to the second part of this problem. And in the second part of this problem, we saw that, or we are told that we are at steady state. We're told that we're at steady state with no heat generation, focusing on the radial direction. So what does that mean? Steady state, this goes to 0, no heat generation, 0. Thermal diffusivity is going to be constant, right? And then focusing on the radial direction, well, that's this term here. So we can cancel out these other two terms. So what we're left with is 0 equals d dr r squared dt dr times 1 over r squared. And then we can rewrite this equation, right? That'll be d dr dt dr equals 1 over r squared times r squared dt dr ddr, sorry, right? And so this is what we're going to be working with. Now we can look at this. We'll bring this over, right? So we have our dt dr times r squared equals ddr times r squared dt dr, right? And so what we're going to do here is we're going to call this our constant of integration, right? So this will be C1. And so then when we rewrite this equation, we'll get dt dr equals C1 over r squared, right? And so what we want to do from here is we're going to integrate. So we'll integrate from some initial temperature to some final temperature, and then from some initial radius to our final radius. And when we do this, we get our T final minus our T initial equals our negative C1 over our evaluated from initial to final, right? And so we'll get our delta T equals negative C1, but we're going to change this, right? So it's going to be C1 and it'll be R initial minus R final. And then we can solve for C1 here and we'll get that C1 equals we'll get C1 equals delta T over 1 over R naught minus 1 over R final, right? And so what we want to do now is we want to relate this to Ohm's law, much like we did before, right? Because we're going to try and find our thermal resistance, right? So Ohm's law, we have our delta V equals our current times our resistance. How we related it before was Fourier's law, right? So Q equals minus K A dt dr. And so with this, we know that for a sphere, right? Imagine this is spherical, right? Our area is going to be 4 pi r squared, right? That's our area. So we can plug that in, right? We'll get Q equals minus K times 4 pi r squared, right? And then if we look back at our equation here, we know that dt dr equals C1 over r squared. Well, we just found our C1, right? So this is going to be, I'm going to write this as the C1 over r squared is 1 over r squared. But we get, right, our delta T over, right, our delta T over our 1 over R naught minus our 1 over R final. When we do this, we see that our R squared cancels out, right? And so we're left with Q equals minus K 4 pi times delta T over 1 over R naught minus 1 over R final. And then we can rework this equation, right, to get delta T equals our Q times 1 over K 4 pi times 1 over our initial minus 1 over our final. And when we compare this to our Ohm's law, right, to our delta V equals I times R, we know that our change in temperature is related to our change in voltage. We know our heat diffusion is our current, or is related to our current. And so our resistance, our thermal resistance, has to be related to 1 over negative 4 pi K times 1 over R initial minus 1 over R final. And so using Fourier's law and Ohm's law, we used our equation for spherical direct coordinates for our heat diffusion, and we found that the thermal resistance related to that would be 1 over negative 4 pi K times 1 over our initial radius minus 1 over our final radius. And that makes sense, right? Our change in radius and then times our essentially our area times our thermal conductivity, right? And so that is all for this video.